also give you permission at that. Yes, cool.
We are recording.
All right, so hello back everyone. We're in the first highlights talk of CPM. Pavel is going to tell us about his stock 2019 paper together with Bartek, right? Computing quartet distance is equivalent to counting 4 cycles. And go ahead, Pavel.
Okay, hello everyone. So first of all, thanks for the introduction and thanks for inviting me. So this is joint work with Bartłomiej Dudek. I should mention that I'm using his slides. So it's about some measure of distance that I'm going to define in a few minutes. And we showed it's equivalent to a very basic problem of counting 4 cycles in a graph. So I guess CPM is traditionally about strings. So we do different things with strings, but not everything can be kind of modeled as a sequence of characters. And sometimes your input is a tree or a bunch of trees. So sometimes a sequence of characters is not enough. So one very natural example in which you really want to work with trees are the so-called phylogenetic trees that capture the history of evolution between species. So you have species, they could be animals or plants or something else. And you would like to capture how they are related to each other. And people consider both rooted and unrooted phylogenetic trees. In this figure, it's an unrooted tree, I guess. And for the purpose of my talk, the trees will be unrooted. So if they're rooted, then somehow you want to say something about ancestry, but this information is not always available. So sometimes you don't have this information. You only want and can capture how similar two species are. So this is the case for unrooted trees. Okay, so those are 2 examples of trees. So please keep in mind that the trees are unrooted and the species are at the leaves. So each leaf is a distinct species. So now I've been told that there are some tools that allow you to recover this tree from the genomes. So I'm not really an expert, so I don't want to go too much into that direction, but I've been told there are tools. Okay, so you plug in your data and you obtain a tree, a possible tree. But of course, maybe you have some noise in your data, or maybe actually have many tools and they will give you different results. So probably in the end, you want to somehow combine these results or at least compare them. So the first question before you get to kind of combining the results is probably that you'd like to compare 2 trees. So you are given 2 trees on the same set of species. So each species, every species is in every tree. And you would like to figure out if those trees are actually almost the same, because you had some noise and maybe there is some small difference, but they're essentially the same. So the first step would be to define some kind of measure of how similar 2 trees are. Now, I don't have this on the slide, but if the trees are rooted, there is a very basic notion of similarity called triplet distance. So in triplet distance, you consider triples of leaves. So recall that you have the same leaves, the same species in both trees. So you choose 3 species and you check what's the shape that they induce in both trees. Okay, so there are 3 possible shapes. And you count how many such triples are the same in both trees. That's the measure for rooted phylogenetic trees. And this is a good measure because, so one reason that I'm aware of is that if you give me all triples in a tree, so for every possible triple, you will tell me what's the shape, I can actually recover the tree. So they fully define the tree. This is not really the case for unrooted trees. So if you take any triple of leaves, you will get the same shape, right? Because there are no directions on the edges. So for unrooted trees, you actually have to look at the quadruples of leaves. You choose 4 leaves and you check what's the shape induced by 4 leaves. And again, you have the same property, well, not the same, a similar property that a tree is can be actually recovered from the shapes defined by every 4 leaves. So that's why people think that it's a good measure. At least that's my understanding. Okay, so now we have 2 trees, and so those are 2 examples, and it's the same set of leaves, just A, B, C, D. And you look at every possible quadruple. So you take every 4 leaves and you check what's the subtree that induced in both trees. So when you think about those shapes, so this is an example. You have a slightly larger tree on A, B, C, D, E, F. And for example, you take quadruple A, C, D, E, and you check what's the induced shape. I will say that it's a shape or a topology that's being induced by those 4 leaves. So in this case, you get something like that. And when you think about it, actually there are 4 possibilities. So if you consider leaves A, B, C, D, then well, the 4th possibility is that they all meet at the same node. So there is a node of degree 4, and those 4 leaves intersect there. Okay, and the 3 remaining possibilities is that you have 2 leaves, let's say A, B, and they meet first, and the leaves C, D also meet first, and then they all meet together. So you have all those possible shapes. So I don't want to define this formally, but I think it should be clear what I mean by this induced shape. So just keep in mind, in your tree, each of those edges actually consists of many edges. Okay, so it's an induced shape. So each of those is actually possibly many edges. Okay, so you have those 4 possible shapes, 4 possible topologies. But now the idea is that we have 2 trees that we want to compare. The set of leaves is the same. So we consider every possible quadruple, so every quartet of leaves, and we count for many of those. The shapes are different in both trees. So that's our measure of how different the trees are. So it's how different they are, not how similar they are, but it's complement, okay? So as an example, if you consider those 2 trees, T1 and T2, on leaves A, B, C, D, E, then when you think about quadruple A, C, D, E, they induce the same shape, okay? Because A and C meet first in both trees, and on the other side you have D and E. So it's the same shape, even though, here it's 1 edge, right? And here it's 2 edges actually in the tree, but this is not important for us. Only the shape is important. Okay, so for A, C, D, E, we don't increase the score, but for A, B, C, D, the shapes are actually different, okay? Because here A and B meet first, but in T2, A and C meet first, okay? So the shapes are different and you increase the score. So it's not us who came up with this notion of distance. So it's actually a well-known distance, and people want to compute it efficiently for 2 trees on n leaves. So the baseline is an n to the power of 4 algorithm. So it works for unbounded degrees trees. So it's not important how large are the degrees. And then there were quite a few papers that considered bounded degree trees. I will say binary trees, but actually because they're unrooted, I mean degree 3. Okay, so binary here means degree 3. So there was n to the power of 3, then n squared. I'm sorry, but I will not read all the names because I didn't remember them. So if you are here, don't be offended. Eventually, there was a paper that gave n log n time error for binary trees. So this is maybe not optimal, but quite close to linear. So very nice. So that's for binary trees. And there is a reason this works for binary trees and orthogonal trees. I will not get into details. So there was a separate line of work. Of course, some of the ideas were similar for larger degrees. So it turns out that for any constant degree, there is n log n time algorithm. Or you can use some kind of matrix multiplication. So that's where the exponent comes from. And finally, there was the d times n times log n time algorithm for degree d trees. But now it might be the case that d is quite large, close to n, and in such case, this is quadratic, right? So now you have the question, is quadratic the right time bound? I mean, we have all those nice results in the fine-grained complexity. So sometimes we have tools that allow us to say that probably you cannot go below quadratic or some other complexity, so maybe you could use one of those tools to show something like that. So we show that the answer is yes and no. So it's no because actually there is a faster algorithm. So we show that there is n to the power of 1.48 time algorithm. I will explain where the exponent comes from, but maybe some of you see this already. And it works for unbounded degrees. So d is not important for this result. And we also show something that depends on d. So the point here is that the dependency on d is sublinear. Okay, and there's some plus something small. Okay, this is not the main point. We want to focus on the case of unbounded degree. Okay, so that's one part of our result, and the other result, the other part is that, well, you might hope to improve this complexity. Looks a little bit weird, right? So it really cannot be the optimal algorithm. So we say that okay, maybe this is not optimal, but there is some limitation on how far you can push this result. So we show that assuming some conjecture that I will define in a minute, you cannot go below n to the power of 4 over 3. Okay, so you cannot decrease it to n log n as for the binary case. Okay, so this is the what we show, and it's all showed by connecting the complexity of computing the quartet distance to a different problem that's, I guess, more fundamental. It's a basic graph problem. It's defined as follows. So you are given a graph. It's a simple and undirected graph, and you want to count simple cycles of length 4 in the graph. So just an example, for the graph on the left, you have 3 cycles because you can go around the square, or you can go around everything, or you can go like that, okay? So it's 3. And for the graph on the right, the answer is 1. So there are just 4 nodes. There is not much you can do. Okay, so you're given this graph. It's on n nodes and m edges. So we will use both n and m. I will explain more in a minute. And we want to count simple cycles of length 4. And you can see that it's a basic problem. I mean, I guess the even more basic problem is counting triangles in a graph, but this is the next step, okay? And people look at different versions. So the basic algorithm is n to the power of 3. You just iterate. And then there was a paper that showed that you can count 4 cycles using matrix multiplication. So you get something subcubic. And if your graph is sparse, so if you care about the parameter m, then you can detect a 4 cycle in m to the power of 4 over 3, which is the same exponent as in the previous slide. So you can guess that there will be some connection between that. So this is for finding. There is a difference between finding and counting that I will try to explain a bit more. And there was later a paper, well, the same year, I'm not sure, but the conference version, that showed that you can actually you can detect a 4 cycle faster in quadratic time. And there was a recent paper that showed that you can count 4 cycles in m to the power of 1.48. It's the same exponent as in the previous slide. But now m is the number of edges in the graph. Okay, so when the graph is sparse, we are better off using this result. And actually later there was a paper that generalized this to this result, m to 4 over 3, for all even cycles. There is a difference between odd and even cycles. I will not get into it, but just maybe look at those papers if you're interested. Okay, and in this paper by Euster and Zwick, this quadratic time algorithm paper, they said that maybe there is no faster algorithm for detecting, for finding. Of course, this only makes sense when your graph is not so dense. So m is smaller than subquadratic. So you need to read your input. And in this later paper by Dalkart et al., they showed that this assumption, this conjecture, actually implies that you will not obtain an algorithm that's faster than m to the power of 4 over 3 for detecting 4 cycles. And this is because, roughly speaking, if your graph is dense, for sure it contains a 4 cycle. You don't have to do anything. You just say yes. And otherwise, you run some kind of algorithm. Okay, so that's the basic idea. So there is this conjecture. So I would call this the conjecture that there is no faster algorithm for detecting 4 cycles. And we show the following. So we establish a chain of reductions between computing the quartet distance and counting 4 cycles in a simple graph. So we go through some intermediate problems. I will show some of them to you. And all reductions are up to log factors. So we are losing logs and some constants. But the bottom line is that this allows us to reduce quartet distance to counting 4 cycles in a graph and the other way around. Okay, so just as a warm-up, so we have a chain of reductions, and a very simple reduction from this chain is that we show that if you want to count 4 cycles, I will use the figures to talk about counting some shapes in a graph. So if you want to count 4 cycles in a simple graph, this can be reduced to counting 4 cycles in a bipartite graph. Okay, so just to show you how this reasoning works. So the input is a simple graph, and you want to construct a bipartite graph, okay, in linear time, hopefully. And from the number of 4 cycles in the bipartite graph, you want to be able to recover in linear time the number of 4 cycles in the input graph. Okay, so that's the idea. And the reduction is very simple. You take every node and you duplicate it. So every node U appears on the left and on the right side of your new bipartite graph. And if you had an edge UV, that it becomes 2 edges. Okay. So that's the idea. And now you can see that this increases the number of cycles by a factor of 2 because you have 2 copies. So you have to divide by 2. So it's a simple reduction. Okay. So now something more complicated. So generally speaking, our goal is to count cycles of length 4. But before we do that, we have to look at all possible shapes created by 4 edges. So not only cycles of length 4, but also 4 independent edges and also more crazy shapes. So just to give you some idea, this is one of those shapes that we want to count. So those are 4 edges and they share the left endpoint. Again, recall that now the graph is bipartite, okay? So there are left nodes and the right nodes. If you want to count occurrences of this shape, there is this simple formula. So for every node, you have to compute the degree, choose 4, okay? And that's the exact number of occurrences of this shape in the graph. So some shapes are simple to count. For the others, there are some more complex formulas. So this is just an example. Please don't try to read this. So you need some case inspection to connect number of occurrences of different shapes with each other. Okay, and for some of them we will have simple formulas, and for others it's not clear if we have a simple formula that allows us to compute the number of occurrences in linear time. So the conclusion is that we figure out that there are 2 types of shapes. Some of them can be counted in linear time. So you have some examples, but again, please don't try to read the formula. It's some simple formula, okay, depending on the degrees. You can evaluate it in linear time in the number of edges of the graph because you are summing up over all edges. And other shapes turned out to be equivalent to counting 4 cycles in the following sense. So the number of occurrences of 4 independent edges is equal to something that can be computed in linear time. So it's some kind of garbage part that I didn't write, plus the number of 4 cycles. So we have a bunch of formulas. There is something that's easy to compute, plus the number of 4 cycles times some constant multiple, plus or minus. Okay, so there are two types of shapes. And this allows us to reduce counting 4 cycles in a bipartite graph to computing the quartet distance. So it's one side of the reductions. So as a consequence, we will say that computing the quartet distance cannot be too easy, okay? Because you can use it to count cycles in a bipartite graph, and this can be used to count shapes, to count cycles in an arbitrary graph by this first reduction. So this reduction is very natural. So you take your graph and you create 2 trees, T1, T2. There are roots. Nodes on the left become children of the root in T1, and nodes on the right become children of the root in T2. Okay, and now if you hit an edge A connecting quadrant 5, you add a leaf with label A connecting it to 1 and 5 on the other side. So that's the whole reduction. Okay, those are the 2 trees. And now we have to analyze what's the quartet distance between those 2 trees, and actually we look at the complement. So we look at how many shapes disagree. And then there is some case inspection, so I'm not going to do this, but just if you go over things carefully, you will obtain this formula, okay? In particular, when you think about a cycle in the input graph, so this is a cycle B, D, F, E, that it corresponds to choosing those 4 leaves, 4 labels, and you can see that they induce a different topology, okay? Because here B meets with E, and here B meets with D. So in the quartet distance, you will have something plus the number of 4 cycles. And then it turns out that this something can be computed in linear time. So it consists of simple shapes, okay? So this allows us to say something about computing quartet distance. So what we say is as follows. You can reduce counting 4 cycles in a graph with m edges. The reduction takes linear time, and it's to computing quartet distance between 2 trees on all of m leaves, okay? So that's the reduction. And now if you believe that there is no algorithm that detects a 4 cycle faster than in this complexity, then there is no algorithm that counts 4 cycles. So there is no algorithm that computes the quartet distance between 2 trees on n leaves in n to the forward tree. Okay, so that's one side of the reductions. Okay. So now that's one side, one direction, and we would like to show the other direction. So we want to establish equivalence up to polylog factors. So we would like to take quarter distance and reduce it to counting cycles in a graph or in many graphs, okay? So this is more complicated, and it consists of a few steps. I will highlight some of them to you. So the first observation is that actually these shapes, so I will call this is a star, and I don't have a nice name for those shapes. So the other shapes actually can be counted in n log n time using the previous algorithm. So the previous algorithm was stated for binary trees, but actually it counts those shapes for arbitrary trees if you analyze it. It's actually written very explicitly. Okay, so we only have to count stars. So we want to count stars that occur in both trees. Okay, so now it's how many shapes are the same, not how many shapes are different. So one idea, which is not really very efficient, but just to start something with, is as follows. So in a star, you have this central node. So fix the central node in the left tree, call it C1, and let's fix the central node C2 in the right tree. And now we want to count stars, shared stars that are defined by those that define C1 and C2. Okay, so those are the central nodes, and this can be nicely formalized as a bipartite graph. So you look at the edges adjacent to C1 and C2, and they become nodes on the left and on the right. And now you look at the subtree. So let's take this subtree, okay, of node 1 here, and this subtree of node 1 prime. You count how many labels occur here and there. So you compute the intersection, and it's 2. There are 2 labels. So you add an edge between 1 and 1 prime, and the multiplicity of this edge is 2, is how many labels are shared, okay? And now you can see that counting shared stars with central nodes C1 and C2 is just counting 4 matchings, so 4 independent edges in this new graph, okay? But with multiplicities. So you have to take the multiplicities into the account. So this is not hard to see. Okay, that's the basic idea, but it's not, you have to work a little bit to use it, because first of all, you cannot really go over every pair of central nodes. That's n squared, that's way too high. And you need to control not only the number of subproblems, but also the total size of subproblems, because in the end you will have those graphs and you want to do something for the graphs. Okay, we show how to overcome this. I will not get into this part at all. We use some kind of recursive decomposition. If you know top trees, we use top trees decomposition, and heavy light decomposition that I guess more people know, and some range queries to count the number of shared labels in the subtrees. Okay, so we convert we work with points in the plane and we count something. So in the end, the conclusion is that we can reduce counting all shared stars to multiple instances of counting matchings of size 4 in multi-graphs. So you have multiplicities, but the total size of all the graphs is n with a few log factors, I guess 2. Okay, but this is counting matchings of size 4, not counting 4 cycles, and it's multi-graphs, not simple graphs. So we're not done yet. So we have to finish this chain of reductions. And just to make sure that we're on the same page, when I say that I want to count 4 cycles in a graph or 4 matchings, I mean that you take the shape and you multiply the multiplicities. Okay, so here it's 30. Okay, so we want to count 4 matchings, but by the previous argument and the classification of shapes, it's equivalent to computing 4 cycles. So we actually count 4 cycles in a graph with weights, and we proceed in 2 steps. So first we say that if you have large multiplicities, actually you can reduce them to small constant multiplicities at the expense of introducing polylog instances. And then we show how to remove the multiplicities at all. So we have just simple graphs. And I will first show you the second step because it's a bit simpler. So we have a multi-graph with multiplicity bounded by constant C. And you want to reduce counting 4 cycles in this graph to counting 4 cycles in a simple graph. So the idea is to multiply the nodes. So a node becomes C nodes, okay? And you connect them with edges appropriately. So you take a copy of a node, and so if you had an edge UV with multiplicity 2, you take every copy of U, and you connect it to the corresponding copy of V, but also to the next copy of V. Okay, so there are C copies that you connect the current copy of U. And when you analyze things, I mean, it's easy to see that you blow up the size of the graph by constant factor because C is constant. And the number of cycles increases by roughly a factor of C, because it's up to you which is the copy that you start, and then it's then it's fixed. But it's not exactly true. There is some additional part that you need to cancel out. The additional part is that you will create new cycles in this graph that don't really correspond to simple cycles in the original graph. So you have to analyze this carefully. So the idea is that in the new graph, you might have a cycle that goes from a copy of U to a copy of V, and then to a copy of the same U, and then to a copy of the same V. Okay, so that's one case. So you use 2 copies of U, 2 copies of V, or you use 2 copies of U and some other nodes V and W. Fortunately, those cycles are easy to count in linear time, so you can subtract them from the result, okay, and then divide by C, and this gives you the result. Okay, so we show that you can remove the multiplicities if they are constant. It was important that the multiplicity was constant because we increased the size of the graph by a constant factor, okay? Okay, so now it remains to show how to reduce large multiplicities. They could be even up to n, when n is the size of the input tree. And somehow you want to create more instances, but with constant multiplicities. So the idea is to somehow group the cycles. So let's say that you want to count 4 cycles such that its edges have multiplicities 3, 5, 8, 10. So you fix the multiplicities that you want to consider, and you will iterate over every combination. So you can capture that by introducing coloring of the edges. So we have seen some color coding technique in the morning. This is not exactly this, but okay, maybe there's some connection. So we color the edges of the graph with colors 1, 2, 3, 4. So they correspond to the current multiplicity. If it's a different multiplicity, then it's bottom. Okay, so you have a graph with 4 colors. And then we want to compute FK, A, B, C, D. It's the number of 4 cycles in this new graph with exactly A edges of the first color, B edges of the second color, and so on. So you want to compute this quantity. And it turns out that you can compute this, so you can reduce this, compute this FK, A, B, C, D to constant number of black box calls to counting 4 cycles in multigraphs with small multiplicities. And this is done using polynomial interpolation. So you create, you somehow take the edges of each color and you create a few copies of this edge and you calculate something. This defines a polynomial and to interpolate back the polynomial. Unfortunately, the constant becomes quite large. It was shown on one of the previous slides. The constant is shown here. Yes, so it's yes, it's not small, but we didn't try to optimize. Okay. So this is an idea how to compute this FK ABCD when you know the multiplicities. And now you could iterate over each quadruple of multiplicities. Okay, but this is too small. Sorry, this is too large because you could have every multiplicity could be distinct. So now the idea is to represent each multiplicity as a power of 2 and operate on powers of 2. So guess a multiset of powers of 2. You will get only log to the power of 4u groups. On each of them, you will apply this reasoning with polynomials. This turns out to be a little bit tricky. So if for the current set of powers of 2, no edge contains 2 powers of 2, you obtain this previous problem. But I didn't show you the proof, but it's crucial in the proof of the previous statement that the graph is simple in this colorful cycles problem. So if on an edge you have 2 powers of 2, then it's not a simple graph anymore. You will have 2 edges with 2 different colors, and the previous reasoning doesn't really work. So you have to do something slightly more technical. So actually you fix not the powers of 2, but multisets of powers of 2. I will not show you how this is done exactly because I'm running out of the time and I don't have slides for that. So in the end, we reduce multigraphs to polylogarithmic number of instances of counting 4 cycles in simple graphs of m edges total. So to summarize, we show chain of reductions, well, a ring of reductions actually. And it means that if you have an algorithm that works in n to delta time for computing the quartet distance, then you have an algorithm for counting 4 cycles in a simple graph on m edges in m to delta time. Okay, so then it means that probably you will not go below n to 4 over 3 for quartet distance unless there is a very nice breakthrough for counting or even detecting 4 cycles in simple graphs. It's a very basic problem. People were not able to go below that. In the other direction, we show that counting 4 cycles in simple graphs on m edges in m to delta time gives you an O tilde n to delta time algorithm for computing the quartet distance. So we lose many log factors and the constant is large, but we didn't try to optimize. So when you plug in the fastest known algorithm, it works in n to 1.48 time for counting 4 cycles. and at the same time n to 1.48 for computing the quarter distance. So this exponent comes from matrix multiplication. Okay, and if someone comes up with a faster algorithm, we'll have a faster algorithm for computing the quarter distance. So I'm out of time, so thank you for the attention, and if there are questions, I'm happy to try to answer.